So let's take a look at this one and begin with highlighting some key parts in the description. So it says redox titrations using potassium manganate in acidic conditions can be used to analyze reducing agents. So there's manganate acting as the oxidizing agent. So that means it's going to be reduced. A student analyzes a solution of peroxide using a redox titration with potassium manganate under acidic conditions. The overall equation is there. The student diluted 25 of a solution of peroxide with water and made the solution up to 250. Okay, so now this is where I'm going to start drawing the template which I've used in many of my other videos on this topic. So what happens is you begin with some sort of sample, and that sample can be a solid or it can be a liquid. In this case, it's a liquid. How do I know? Because it tells me right there it's a solution of peroxide. And then that is made up into a standard solution in a volumetric flask so that you can actually repeat the experiment, as I said. So if we just carried out an experiment using 25 of peroxide, that number there, you'd only be able to do it once. But if you make it up to 250, well, you could probably do it 10 times if you wanted to. So the original volume of the solution is 25. And then that is put into a volumetric flask. You may have seen these in the lab, like a round bottom like that with a thin neck. And on the side is like a measurement scratched out saying where you should fill the water level to make up the exact solution. So what we got here, that's 250. Okay, so you add 25 of this peroxide into the volumetric flask and make it up to 250. The student then titrated 25 of the solution against potassium manganate. So they're taking 25 of this. So there's the flask. There's the burette. And then in the burette is the potassium manganate, of which we know that the concentration is 0.02 dm cubed. And the volume used to react with the peroxide is 23.45, sorry. Why are these described as back titrations? Well, if we call the sample number 1 and then the oxidizing agent number 2, 1 and 2 will react together in this pot to undergo a redox reaction. This redox reaction is that there. There's the equation. So that equation there is taking place in the conical flask. Now, the reason why it's called a back titration is because, well, this is the start and this is the end. And what you have to do is you literally work backwards, as I've described in my other videos, from the end to the start to get information about the sample that you want, which in this case is they want a concentration. So C is the question mark. They want the concentration of this peroxide. So we're starting at the end because we know information about the potassium manganate, and then we're going to go back to the start to get information about the peroxide. So make sure you have your periodic table at hand and calculator as we can do this together. So the first thing I'm going to do is I'm going to work out the moles of the potassium manganate. So let's call this A, because that is where I start. I start at the end and I only have information on the potassium manganate. So moles equals C times V. Concentration is 0.02 times the volume. Now the volume must be turned into decimeter cubed. And the reason why that is because the standard unit for concentration is moles per decimeter cubed. But volumes are always supplied to us in questions, well, most of the time, in centimeter cubed. So we've got to turn them into decimeter cubed. So that becomes 0.02345. Gives us an answer of, for the first step, 4.69 times 10 to the minus 4 moles. So that's the number of moles of potassium manganate that's reacted in the conical flask. Part B, the next bit, we've got to work out the moles of peroxide that it's reacted with. So to do this, we use the molar ratio. The molar ratio, you can see, I'm just underlining here in blue, is 2 to 5. So 2 lots of potassium manganate react with 5 lots of peroxide. So therefore, to get my moles of hydrogen peroxide, I have to divide my answer by 2 and then times it by 5. Now that is the number of moles in a 25 centimeter cube sample. in the 25 centimeter cubed flask. How do I know that? Because it tells me that 25 is taken from the 250. So now the next thing I need to do is, we're going to start going backwards. We need to go back to this point now, the standard solution. So we want to find the moles of H2O2 in the SS, the standard solution. So to do that, you can see 25 is simply a tenth of 250. So this 10 times, it's come from 10 times as much moles in the standard solution. So all I have to do for my answer is just times it by 10. Right, so now that we have the moles of the peroxide in the standard solution, the next hour, as I've just drawn it there, is to find out the moles in the sample. Well, the moles in the sample is also 0.011725. The reason why is because all I did was take the solution, the original sample, I put it into an empty round bottom flask, and then they filled it to the top of 250. The amount of moles has not changed. You've just added water on top to dilute it. So the moles is the same. So finally, E, the original concentration, is going to be moles equals CV. So C equals moles over V. The moles we just did, 0.011725, divided by the volume that was originally put in, which I'm just circling here. So 25 was put into that solution, gives me a final answer as the original concentration of peroxide. Now, look at the bullet point there. It's asking for the concentration in grams per decimeter cubed. But in order to get that answer, you have to work it out in moles per decimeter cubed first, which is what I just did there. So the final step to get to that, F, is to turn it from moles into grams. It's really simple. You take your answer for in moles per decimeter cubed, and you simply times the moles bit by the RFM. So mass equals moles times RFM. So I'm just using the moles formula. You don't need to worry about the decimeter cube bit. It stays the same. So then mass equals moles times the RFM. So it'll be 0.469 multiplied by the RFM of hydrogen peroxide. And that gives me a final answer of, so that is the original concentration of hydrogen peroxide that was used in this redox titration. Next one. What volume of oxygen gas measured at room temperature and pressure would be produced during this titration? What we need to do now is go back to the molar ratio of the conical flask, and you can see 5 moles of peroxide, so just circled there, produces 5 moles of oxygen gas, right, during the redox reaction in the flask. Now, I worked out the number of moles of peroxide in the flask at this point. It's there, 1.1725 times 10 to the minus 3. So that's what I'm going to use. So the molar ratio you can see there, 5 to 5, is the same as 1 to 1. So G, so the moles of O2 is that number there, 1.1725 times 10 to the minus 3. And to turn that into a volume, I'm just going to use this approximation, which is the gas approximation. So moles equals V over 24, which means that 1 mole of a gas occupies approximately 24 decimeter cubed at room temperature and pressure. So therefore V will equal, gives me an answer of, so that's 0.028 decimeter cubed. Or in other words, to put it into centimeter cubed, times it by 1,000, is 28 centimeter cubed, which is a really sensible answer because look at the quantities we're dealing with. 25 of peroxide, 23.45 of potassium manganate. So always do a check at the end and think, right, is this a sensible answer? You know, if I had 500 or just 4, then I'd have to relook at my calculation and see if I'd made a typo by missing out a factor of 10 or something like that. Now, instead of using that, this is worth mentioning, we could have used the ideal gas equation, which is PV equals nRT, and had a better answer. But I decided to go with this one just to show roughly, you know, the process of how it works. Okay, so select the correct equation depending on what you've been told in class. Okay, that's it. I hope that's helpful. If you are stuck at any part of this or the other ones I've produced, the other questions in the other videos I've made, please just comment down below and I'll get back to you and help you.